We have atmospheric air at 25 degrees C, and I'm going to try and write. It's adiabatically compressed in a piston-cylinder apparatus to a final pressure of 800 kilopascal. State 1, it's compressed to 2, and then after 2 there's a new state where it will be cooled. The air is then cooled to 25 degrees C at constant pressure. So the first question is, what's the initial humidity ratio? What's omega 1? Given the temperature at 1 is 25 degrees C, and the relative humidity at 1 is 70%. So what do? You come over and you say, well, I get to P sat at the temperature 1 at 25 degrees C. To get PV, I multiply the relative humidity at 1 times the saturation pressure at 1. So now I have the partial pressure at 1 for the vapor. And then I get the dry air partial pressure, the total pressure at 1 minus PV at 1. And then I calculate the humidity ratio at 1, 0.622, PV1. This is the total pressure at 1, right? Divided by the partial pressure of the dry air at 1. All that makes sense? Now, after compression, we'll call that state 2. It's been compressed, the pistons now made the volume much smaller. And what happened to the pressure at 2? It went up to 800 kilopascal, didn't it? What was the pressure at 1? Atmospheric pressure. So it's 101.3 kilopascal. For part B, what is the temperature in degrees C? So what's the temperature at state 2? Is it going to be greater than 25, the same as 25, or what? What do you expect? Greater. How are you going to calculate it? It's all, the whole chapter is ideal gas. The vapor behaves as an ideal gas. The dry air behaves as an ideal gas, and it's compressed from one pressure to another pressure. How are you going to calculate the temperature T2? It doesn't say it up here. It says it's adiabatic, but if it would also been reversible, that would have been perfect. Adiabatic and reversible, so what we'll do is we'll assume it's reversible. And because it's adiabatic and reversible, we know it's isobaric, no. Isothermal, no. Isentropic. And then we have a nice analytic expression that the final temperature is equal to the initial temperature. Both those temperatures have to be an absolute temperature, not relative, have to be in Kelvin, not degrees C, is equal or multiplied by the ratio of pressure to the K minus 1 over K. Now, I know we can do a whole lot of work to get K, but when you calculate the humidity ratio at state 1, the humidity ratio at state 1 is 0.0139. Tell me, what is the mass fraction of water, roughly, in this system? 1%, right? It's 0.0139 is humidity ratio, so its mass fraction is about 1%. It's small. You just think about it's primarily dry air. Let's calculate it with the K of 1.4. Cold air, use 1.4. Now you say, I want to use variable specific heats. That's going to be the next improvement to get a better answer for T2, because K isn't 1.4 at those elevated temperatures. So anyway, you can calculate T2 using this 1.4, and you'll get it like 538 Kelvin, or the temperature 2 is around 265 degrees C. So it's quite high. I didn't go back and improve K based on elevated temperatures, nor did I go back and improve K based on a mixture of water vapor and dry air. But I did assume it's isentropic compression. Now for part C, what is the humidity ratio omega 2? I'm going to pause and I want you to give me an answer for that. All right, so what we find is that the relative proportion of vapor to dry air didn't change. I didn't take some vapor out or add some vapor. I didn't take some dry air out or just add. I know I changed the pressure. I know we changed the volume, but omega 2 is equal to omega 1. It's the same numeric value. So that's how you get the answer to part C. What about D? What about the relative humidity? Phi. I'm looking now for phi at 2. So the relative humidity at 2. First of all, the relative humidity at 1 was 70%. Try to guess. Did it go up, stay the same, or go down? And why? So I'm going to pause and I'm going to come around and see how you do on part D. All right, so there's about 4 ways, there's probably even more ways to make this work. But what I need to do is I need to find PV at 2. And I need to divide it by P sat at 2. True? All right, now the temperature went way up, did it not? So what do you think about the partial pressure maximum, the saturation pressure at this tremendous temperature? T2 is 265 degrees C. It's way up. It's way up. So now you're dividing by a large number, and it's the relative humidity at 2 is very low. Psat at 2 is like 5,071 kilopascal. What about the partial pressure at state 2 of the vapor? Partial pressure of the vapor at state 2. You could. I know that some people would say, look at omega 2, 0.622, PV2 divided by P2 minus PV2. It'll work. It'll definitely work. Another way to do it is you just look at the mole fraction of the vapor initially at 1. Is the mole fraction of the vapor initially at 1 the same as the mole fraction of the vapor in the mixture at 2? And isn't the mole fraction ratio of the partial pressure divided by the total pressure? Isn't that the partial pressure divided by the total pressure? The total pressure was now 800. It started at 101. The PV, we already calculated right here at 1, so you can get PV2 that way too. Will you get the same answer? You better. It better get the same. Does it look like they're going to get the same answer? No, it looks like it's a completely different route. It really does. Okay. And then somebody else said, well, why don't we just come back to the same equation that we used before, and let's go P V2 divided by PV1 is equal to T2 over T1 to the K over K minus 1. Kind of like the equation we used to get the temperature to. That'll work too, right? Because the mixture of the vapor was isotropically compressed, but the component was isotropically compressed as well. So you get the relative humidity to be Phi2 to be a whopping 0.35%. It's not 35%, less than 1%, less than 0.5%. At that high temperature, you can hold a lot more moisture than what's in there. But now we cool it. So we read on now for part E and F. The air is cooled to a temperature, T3, of 25 degrees C. It's happening at constant pressure. So I know that it's an ideal gas, so probably that piston's going to squeeze it a little more to keep it at constant pressure. After the cooling, determine the relative humidity, Phi3, and the humidity ratio, omega 3. Let me let you work on that for a minute, okay? How are you going to solve for Phi3? How are you going to solve for omega 3? Let's calculate the dew point temperature at state 2. And if that dew point temperature is above 25, as I'm cooling it, I'm going to hit and I'm going to start dewing out. I'll still cool it. More and more will dew out, right? But until I get down to 25 degrees C. So what is the dew point temperature at state 2? How do I calculate that? It's equal to the saturation temperature at the partial pressure, the vapor partial pressure. What is that vapor partial pressure at state 2? That was this one right here that you calculated. And that vapor partial pressure at state 2 is 17.5 kilopascal. And when you look up the saturation temperature at 17.5 kilopascal, you find that the dew point temperature is 57 degrees C. So I'm going to cool it. When I hit 57, what do I know about the air? It's saturated. If I cool it to 55, it's still saturated, but some liquid's collected at the bottom. If I cool it to 40, if I cool it to 30, more liquid collects at the bottom, but does the air stay saturated? With that information, now tell me, what is the relative humidity at state 3? I'm going to pause and walk around. The psychrometric chart's in your appendix. It's figure A9 that's in the appendix of the textbook. When you start looking at something like this, read what the figure says. And as you read, there's something very important. What's very important in the label? That it's good for how many ATM? 1 ATM. You start changing the total air pressure, and you may not use this chart. Don't use this chart. And that problem I just gave you where you're looking at a compressed air system at 800 kilopascal, don't use the psychrometric chart. It's only good for 1 ATM. If you do any design work at a mile-high city like Denver or parts of Albuquerque or a lot of cities, or even some other cities that are more than a mile high, you have to get high-altitude psychrometric charts. Or, hey, there's a thing called a computer, and it's been invented since then, and there's a lot of calculate things and then have it plotted in a psychrometric chart for whatever elevation you want to work with. But don't worry, we're at 1,000 feet here. We're far from a mile-high elevation, and it's going to work really well. So when you take a look at the chart, what's on the x-axis? Dry bulb temperature. Now, I know that 50 degrees C is pretty hot. 0 degrees C, that's about what it got down to this morning, right? In some areas, freezing. But does this work? Can you have moist air at negative 10 degrees C? Can you have moisture in air at negative 10 degrees C? Yeah, you can. Doesn't feel like a lot of moisture because it can't hold a lot of moisture at air temperatures that low. But is this moisture, is it really water vapor behaving as an ideal gas, or is it little white flakes that sometimes fall out of the sky at negative 10 degrees C? It's water vapor. It's not water solid particles in the snow or anything like that. You can have vapor, water vapor, behaving as an ideal gas at temperatures less than freezing point or 0 degrees. Okay? Okay. Now let's take a look here. What is on the y-axis, plotted not on the left but on the right? It's the humidity ratio, omega. Look at the units. Kilograms of water per kilogram of dry air. Look good? This has a lot of moisture in it. What's the lowest you can go? Can you go below 0? It doesn't make sense to go below 0. This is dry air, that whole line. You could have dry air at 40, you could have dry air at 10, you could have dry air at negative 10 degrees C. Well, if that's dry air, where is saturated air? Well, that's where it's 100% relative humidity. Can you see the 10% relative, 20%, 30%, 40, 50, 60, 70, 80, 90, 100% relative humidity? Isn't that saturated air? There is a curve above which there's no data up there. Saturation temperature or saturated air, it's 100% relative humidity curve. Got it? All right. So anywhere in between is all of real air conditions where you can actually have a state. It can be that temperature, that humidity ratio, that relative humidity, etc. We have a temperature, dry bulb. We have humidity ratio. And we know where its relative humidity curves are. So we already know the two humidities, omega and phi. But weren't there 3 temperatures? There was temperature dry bulb. Oh, we got that one. Temperature wet bulb and temperature dew point. So I say just like this. I'll say, where's a line of constant relative humidity? You'll say, oh, like this. That's a line of constant relative humidity, right? Where's a line of constant dry bulb temperature? It looks like this. That one's a line of constant 40 degrees C dry bulb temperature. Where's a line of constant humidity ratio? Let's say it's a 0.01. There's a line of constant humidity ratio. True? Now the hard part. Wet bulb temperature. Where's a line of constant wet bulb temperature? What's it look like? That's right, slashed at a diagonal. So this line right here all has a wet bulb temperature of 20 degrees C. This is all a constant temperature of 30 degrees C. Right? See that? Those are lines of constant wet bulb temperature. All right, that was the next to the easiest one, but here's the hardest one, right? Dew point temperature. Dew point temperature. What's a line of constant dew point temperature look like on this diagram? I'm going to pause and then you come around and show me, okay? All right, maybe that question's a little unfair. Show me a line of constant dew point temperature. Let me ask another question. Where, I know I have 3 temperatures. Is there any place on this diagram where the numeric value of all those 3 temperatures would be the same at that state? Where would that state be? Where, if it's possible, you could have the wet bulb equal to the dry bulb equal to the dew point. I'm going to now go around and see if a number of you can answer that question, right? Are there any states where the 3 temperatures have the same numeric value? The dry bulb is equal to the dew point equal to the wet bulb? And if it is, show me those where that state or states would be. I'm going to come around and see what you get. All right, so a lot of people figured out that when the air is saturated, when it's 100% saturated, it's called saturated air. Isn't it at its dew point? Isn't the dry bulb equal to the dew point? And isn't the wet bulb the same as the dry bulb? So all 3 temperatures are the same when it's saturated air, when it's 100% relative humidity. That's all along this line. So let's say I'm at this point right here. What's the dew point temperature of the condition right there? If the moist air is right there, it has a dry bulb of 30. What is its dew point temperature? 30. If the condition of the air is right here, it has a dry bulb of 20. What is its dew point temperature? 20. Got it? So show me a line of constant 20 degrees C dew point. I'll show you a line of constant dry bulb of 20. There it is. I can show you a line of constant wet bulb of 20. There it is. But what is a line of constant dew point of 20 degrees C? There. That's what it looks like. It's completely horizontal. Maybe it's easier to think about this. Start at a point out here. It's not close to being saturated air. What do I do to make it saturated? I don't change the moisture content. I don't change how many kilograms of vapor there are per kilogram of dry air. All I do is cool it off. I drop the dry bulb, drop the dry bulb, drop the dry bulb, drop the dry bulb. As I'm doing that, it's going from maybe 35 to 40% to 50% to 60% to 70% relative humidity. And then all of a sudden, boom, I get over there, I'm 100% relative humidity. And now the dry bulb temperature is equal to the dew point temperature. So anywhere along that line is a constant dew point temperature. Last now is our enthalpy. So our mixture enthalpy, which is the dry air enthalpy plus the saturated vapors enthalpy times the humidity ratio. So everything's per kilogram of dry air. And these lines are projected with that slope. Can you see how they try to show you the slope? So there's a line of constant enthalpy of 40 kilojoules per kilogram of dry air, and it's projected down. It's essentially the same slope as the wet bulb temperature. Slightly different, but close enough to be the same. That's how you would read off the enthalpy. Ready to use the chart? Use the chart, locate where air is at 25 degrees C dry bulb at 50% relative humidity. Then read off humidity ratio, omega, temperature wet bulb, temperature dew point, mixture enthalpy, and specific volume. I forgot to point out specific volume. Specific volume is right here, this line. Its slope right here is a constant value of 0.9. See that? This is a constant value of 0.85 specific volume. Here's a constant value of 0.8 specific volume. And they tell you the meters, the units on it, meters cubed per kilogram of dry air for that specific volume. So, read off those values. Locate the state on the chart and read them off, okay? I've got about 4 minutes left, so let me do this, okay? One thing is you need to get proficient at using the chart. There's another thing you can do is online. A lot of people know how to use the internet with Google and other things. All you have to do is type online psychrometric chart or something like that. Psychrometric evaluator, psychrometric properties. Anyway, the Dayton ASHRAE chapter has one. You can't use this on the exam, but you can check it. You can use this to check your work. On the, like that last question. So all I did was, okay, here's atmospheric pressure, put in 50% relative humidity, put in 25 degrees C, click this button to say calculate. There is the dry bulb and the barometric pressure returned to you, and the relative humidity returned to you, and it returns back also the wet bulb around 18 degrees C. It returns the dew point around 14 degrees C. It returns the enthalpy, 50.3 kilojoules per kilogram. Now, reading the chart, you're not going to get 4 digits. You're good to get 2, and sometimes the students are really good at 3. They really are. They can sometimes get 3 digits. And then the humidity ratio, 0.00988. And then forget about, well, this is the specific volume. I don't think I asked for it, but there it is. Okay. And then test yourself. Change it up. Say, okay, now I change it to 30 degree dry bulb and 50% relative humidity. Go and get those properties again. And in the interest of time, I typed those in. So 30 degree dry bulb, 50% relative humidity. There's the wet bulb, the dew point, the mixture enthalpy, humidity ratio, and specific volume. We'll stop there.